So for today, we'll be talking about the special cases of power series. We call them Taylor and Maclaurin series. Okay, so recall a power series centered at A. It will be of this form. So the sum of Cn times x minus a raised to power n running from 0 up to plus infinity. So of course, x here is a variable, a here it's a fixed number, it's a real number. Cn here, they are constants, they are coefficients of this x minus a to the n. Okay? Last time we were able to obtain the power series representation um, for this function here, 1 over 1 minus x. Okay? Assuming that the absolute value of x it's less than 1, then this guy here, it's just equal to this power series, sum of x to the n from 0 to plus infinity. So take note that if x, or if the absolute value of x it's greater than 1, then this equality will not hold. Okay? If absolute value of x is greater than 1, this guy here will diverge. But of course, this one here, it's still a number. Okay? So the equality will not be true if the absolute value of x is greater than 1. So we only have the equality in this case. And then coming from here, we derive some more um, power series. We got some functions that are represented by some power series. And the equality of the function and the power series is only true given the situation that is similar to this. Okay? Now, question is, or are, do other types of functions have power series representations? So the last time we had 1 over 1 minus x, we had the derivative of this and the integral of this. The integral of this, or similar to this, it's just the logarithmic. So we have the um, this type, we have the logarithmic, we have the derivatives of this. Okay, we actually have arctan, and it can be derived the um, using the identity. We have 1 over 1 plus x squared. Okay, if you recall, this is just the sum, negative 1 to the n, x raised to power 2n, and from 0 to plus infinity. And the equality holds provided that absolute value of x is less than 1. So from here, you can derive the power series representation of arc tan. Okay? You just need to integrate this guy here, and therefore, you just need to integrate this one. And so on and so forth. But for other types of functions, do they have power series representations? And if so, how do we find such representations? Okay? Now, what you will see in the next slides, so they are the way of finding the power series representations of any function, including this, okay, including all the functions that we have discussed from the last time. This is the more general way in finding the power series representations of those functions. Okay? So we will see that in the next slides. So let's see. Suppose we have a function f of x with a power series representation. Okay? So suppose this function f of x can be represented by this power series for absolute value of x minus a less than r. So meaning this function here, it's equal to this function or this power series provided that we have this condition. Okay? So if we expand f of x, we will have f of x equals c sub 0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus etc. for each x satisfying this interval. Okay? Now, if x equals a, okay, if x equals a, of course, these guys here will disappear and everything else here. And we will only have c sub 0. So if x equals a, then f of a equals c sub 0. Take note of that. Now, we get the derivative because from the last time we saw that the derivative of your, if you have a power series representation, okay, you can do the differentiation inside its interval of convergence. Okay? So provided that absolute value of x minus a is less than r, we can do the differentiation. On the left-hand side, we just have f prime of x. On the right-hand side, of course, this constant will disappear. This will just be c1 after differentiating this. This here, after differentiating, will get 2c2 times x minus a. Here, after differentiating, we will have 3c3 times x minus a squared. So we are just using power rule. And so on and so forth. We will have the next term here, 4c4 x minus a to the power 3, etc. And then, if we evaluate the derivative at x equals a again, of course, this will disappear, etc. Everything else here will disappear. What will remain is this c1. So the derivative of f evaluated at a will just be c1. Okay? And then we do the differentiation again. We differentiate this. Okay? So that will be the second derivative of f. If we differentiate this, this will disappear. The derivative of x minus a, it's just 1. So you will have your 2c2. Here, if you get the derivative, the square will go down. Okay? So what we will see is the following. F double prime of x, it's equal to 2c2 plus 2 times 3c3 times x minus a. Then the next term will be 3 times 4 times c4 x minus a squared. Okay? The next term here, it will be 4 times 5c5 x minus a to the power 3, and etc. And then from here, we evaluate again at x equals a. So this will disappear, and we will end up with this identity here. F double prime at a, that's equal to 2c2. Okay? Let's get the derivative of this again. We will end up with this. So f triple prime of x, it will be equal to 2 times 3 times c3 plus 2 times 3 times 4 c4 x minus a. Then the next term will be 3 times 4 times 5 c5 x minus a squared, and etc. Okay? And then we get, we will let x equals a again. This will disappear, and the rest there. So f triple prime of A, that's just 2 times 3 times C3. Okay? Then we differentiate this again. We will be able to find the value of f quadruple prime, or the fourth derivative of f evaluated at A. And that will be some constant times C4, and etc. You do the differentiation, and you will end up with the following. If you get the nth derivative of of f evaluated at A, so the nth derivative of f evaluated at A, it will just be 2 times 3 times 4 times 5, etc. until times n, and then times cn. But this guy here, the product here, it's just n factorial. Okay? That's just n factorial. So if you look at this, you have 2 times 3. That's 3 factorial. If you do the fourth derivative, you get the fourth derivative, you will have this part here. 2 times 3 times 4. That's your 4 factorial. And so on and so forth. So the nth derivative of of f evaluated at A, that's just n factorial times Cn. Okay? Therefore, if we solve for Cn, we will have this. We divide this by n factorial. So we divide this by n factorial. C sub n, that's just the nth derivative of f evaluated at A over n factorial. Okay? What does this mean? The Cn here, this guy here, we can replace that with the nth derivative of A divided by n factorial. So that will be the point of our computation. Okay? So we have the following. If f is a function which has a power series representation at A, so take note of that. If f is a function which has a power series representation at A, then it will be of this form. Okay? It will be the sum of nth derivative of f evaluated at A divided by n factorial x minus a to the power n. N runs from 0 to plus infinity. Okay? And if we expand this, we will have the following. F of a plus f prime of a over 1 factorial times x minus a plus f double prime of a divided by 2 factorial times x minus a squared plus f triple prime of f evaluated at a over 3 factorial times x minus a cubed plus etc. So remember, this is just your c sub 0, c sub 1, c sub 2, c sub 3, etc. Okay? And this guy here, this representation, again, the equality holds only on this condition, under this condition. Absolute value of x minus a less than r for some radius r. So meaning the equality only holds in its interval of convergence, the interval of convergence of this series. We call this series the Taylor series of the function f centered at A, or simply the Taylor expansion. Okay? Take note, This part here is important, centered at A. Because if you have a different center, these values here will be different. And of course, if you have a different center, this guy here, it's not x minus A. Maybe the other center now is B. So it will become x minus B in absolute value less than some other radius. That is your new center, B. So the coefficients here may be different. Okay? Questions? So this is the Taylor series of F centered at A. Okay? Now, of course, we adopt this convention. The zeroth derivative of a function, it's just the function. Therefore, the zeroth derivative of A, it's just your f of A. It's just important to mention that because your n starts from 0. So you might ask me, what is this? The zeroth derivative of A divided by n, or divided by 0 factorial. So from the convention below, that's just your f of A here. And you know that 0 factorial, this is just 1. I mean, that's how we define 0 factorial. So we'll just have f of A on this. Okay? Now, if the center A is 0, okay? If A is equal to 0, we call the series Maclaurin series of F. So Maclaurin, it's just a special case of this Taylor series. Special because for Maclaurin, the center is 0. So if I ask you, find the Taylor series of F, you have to ask me which center. Or I will tell you what will be the center if I ask you to find the Taylor series. On the other hand, if I ask you to find the Maclaurin series of F, automatically the center is 0. All right? Questions? So, let us get some Taylor series representations of this of functions. For example, let's have this. Find the Maclaurin series for the function f of x equals e to the x and determine its radius of convergence. Okay? Determine the radius of convergence. So, we have f of x. This is equal to e to the x, which means f of 0, this is just e to the 0, and this is equal to 1. We get the derivative of f. This is still e to the x. And of course, if we evaluate that at 0, it's still 1. In fact, for all n, the nth derivative of x or f is still e to the x. Which means if we evaluate that at 0, we'll have 1. So what does this mean? C sub n, this is just the nth derivative at 0 over n factorial. And this is simply 1 over n factorial. This means your f of x, okay, which is e to the x This is 1 over n factorial x minus 0 to the power n from 0 to plus infinity. Or we simply write this as the sum x to the n over n factorial n from 0 to plus infinity. Okay? Now notice, instead of writing equality, I just use this symbol. Because the equality is not yet found. What we only have is a possible series representation. The equality can be uh, can be um, can be assured once we know the radius, once we know the interval of convergence. Okay, remember, you have a Taylor series or a Maclaurin series or any series. It will be equal to a function only on certain intervals, not necessarily all the time. Okay? So our next job, determine the radius of convergence and also determine the interval of convergence. We have done this example, I think. We have shown the interval of convergence and the radius of convergence of this series here. So let us just recall. Let's do the solution here again. So this time, our a sub n, we have x to the n over n factorial. We want to find the limit as n approaches infinity of a sub n plus 1 divided by a sub n with absolute values. This is the limit as n approaches plus infinity. Again, we start with the following statement, by the way, for x not equal to 0. Okay? Then let us write a sub n plus 1, that's x to the n plus 1 over n plus 1 factorial times over, so we have the denominator a sub n here. So if we multiply it, we just need to get the reciprocal of this. So we will have times n factorial over x to the n. And then this will become limit as n approaches plus infinity, absolute value. We can write x to the n plus 1 as x to the n times x over x to the n times n factorial over n plus 1 factorial can be written as n plus 1 times n factorial. So I hope you remember what we did in this part. But anyway, let's show that again. So this guy here will cancel, and this guy here, also this and this. So we will end up with the limit as n approaches plus infinity of absolute value of x over n plus 1. And as n approaches plus infinity, this guy here, it's fixed. Okay, it's fixed relative to n. As n approaches infinity, this will be equal to 0, which is less than 1. So by ratio test, okay, the series x to the n over n factorial and from 0 to plus infinity converges for all x. Okay? So the interval will be the set of real numbers. So f of x. This is your e to the x. This is just, we now have the equality. So it's equal to the sum x to the n over n factorial, and from 0 to plus infinity for any x in the set of real numbers. Okay? So this is the Taylor or the Maclaurin series representation of e to the x. Also, radius of convergence, this is infinity. Okay? Next problem. Find the Maclaurin series for e to the minus 2x and use it to find the sum, this sum here. Okay? Now, we can do the same process as in before. We start with f of x equals e to the minus 2x. We get the derivatives and then find whatever we need to find. C1, C2, C3, etc. Or we can use this identity here. Note that the equality is true for all x in the set of real numbers. So if you have this minus 2x here, it's still a real number. So the equality is still valid. Solution. From the previous example, we have e to the x equals the sum x to the n over n factorial, and from 0 to plus infinity for any x in the set of real numbers. So, e to the minus 2x, it means we'll just replace this x here by minus 2x. Correct? E to the minus 2x, this is just the sum minus 2x raised to power n over n factorial. And from 0 to plus infinity, or this will be sum from n equals 0 to plus infinity, negative 1 to the n, 2 to the n, x to the n over n factorial. And the equality holds, again, for any real number x. You might argue, sir, it should be for any real number negative 2x. But remember, if negative 2x is a real number, your x is still a real number. Okay? So you can just remove that multiplier minus 2. Okay? So now we have this power series representation. In fact, it's the Maclaurin series representation of e to the minus 2x. According to the problem, we use this to find the actual sum of this. And look at this guy here. You have negative 1 to the n, it's negative 1 to the n in here. You got 2 to the n, there's 2 to the n in here. You got n factorial here, you have n factorial here. You started from n equals 0, here the starting point is also n equals 0. Okay? So what's missing? This 3 to the n on the denominator. But we have here x to the n, the variable here. So this must be used in order to find that 3 to the n in the denominator. Okay? So we take x equals 1/3. Okay? Then, of course, x to the n, this is 1 over 3 to the n, but this is just 1 over 3 to the n. So, the sum, negative 1 to the n, 2 to the n, over 3 to the n factorial, and from 0 to plus infinity, this is just e raised to negative 2 over 3. So that's the actual sum. Okay? Now, we have seen that if f has a power series representation, then it is given by its Taylor series expansion. Okay? On the other hand, when is it true that the function f of x is equal to its Taylor series? Okay? When is it actually true that this f of x is equal to the Taylor series? Meaning, suppose we are given a function f, okay, and we have obtained this guy here. When do we have the equality? Like I mentioned earlier, um, the equality will be inside the, well, the domain of that will be inside the radius of convergence. Okay? Meaning your x must be inside the interval of convergence. But how are we sure? How are we sure? Let us consider the partial sum t sub k of the series given by this guy here. Okay? So we have t sub k of x. It's equal to the sum from n equals 0 up to k of nth derivative of f evaluated at a over n factorial x minus a to the n. So you'll just have f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared, etc. until this term only. The kth derivative of f at a over k factorial x minus a to the k. So the highest power is just that subscript. We call this the kth degree Taylor polynomial of f about the center A. Okay? About that center A. Now, we say that the function is equal to its Taylor series, okay? If your f of x equals the limit of your t sub k. Okay? The function f is equal to its Taylor series if f of x equals the limit of t sub k of x as k approaches infinity. Remember, you have a series, you have a sequence of partial sums. The sum is equal to the series if the sum equals the limit of the partial sums. That's what we are doing here. And we are doing it here Point-wise. You choose your x, you evaluate, you do this, evaluated at your x. And then you will collect all those x's. That will form your interval of convergence or domain of convergence. Okay? Now, let R sub n to be the error term. Meaning, you get your f of x, you subtract the nth degree Taylor polynomial of f, centered at A, of course. So you get that function. The equality will hold, okay? The equality of your function with the Taylor series expansion will be true if this error function goes to 0. Okay? So notice, limit of Tn as n approaches infinity, it will be this guy here. Limit of f of x minus r sub n of x as n approaches infinity. Okay? We calculate it, we have this. F of x minus the limit of r sub n as n approaches infinity. And from here, okay, from here, the equality will hold if this is going to 0. Correct? So this means f of x is equal to its Taylor series expansion if the limit of the error term goes to 0. Okay? So how do we use this error term? Similar to what we did before when we are trying to approximate a sum using the improper integral test and also the alternating series test. We can approximate values using the Taylor series or the Taylor polynomial of your given function. For example, here, use the fourth degree Taylor polynomial for f of x equals e to the x centered at 0 to approximate the value of e. Okay? Use the fourth degree Taylor polynomial of f of x centered at 0 to approximate the value of e. Solution. We know that e to the x, this is equal to the sum x to the n over n factorial, n from 0 to plus infinity, for all x in the set of real numbers. Now, we look at Tn of x. In fact, we need T sub 4 because we need the fourth degree Taylor polynomial. So this is just the sum x to the n over n factorial, n from 0 up to 4. Okay? This is equal to what? 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. I did not write the factorial here because anyway 2 factorial, it's just 2 times 1, which is also 2. Correct? So if we do this is just 1 plus x squared over 2 plus x cubed over 3 times 2 times 1, that's just 6, plus x to the 4 over 4 factorial. So 4 times 3 factorial, that's 4 times 6, this is 24. We want to approximate the value of e. It means our x is equal to 1. E to the 1, that's e. And we need to use the fourth degree Taylor polynomial. So, e to the 1, this is approximately, okay, approximately equal to t sub 4 of 1. We evaluate it at 1. So this is just 1 plus 1 plus 1 half plus 1 over 6 plus 1 over 24. Okay? At this point, since this is approximation, let us use decimals. Okay? So this is equal to, let's solve this. We have 2.5 plus 1 over 6 plus 1 over 24. So I got 2.708333 dot dot. Okay? That's the approximate value of E. Let us give some actual numbers of E. So your E, this is approximately equal to, let us see, 2.17, 2.71, 2.718281, 8, 284, 59, 045. That's the best that my calculator can. Okay. So in here, you see, with the fourth degree Taylor polynomial, we are only accurate up to the first decimal place here. Okay. But if you get higher degree Taylor polynomial, you will be closer to this value here. Okay? You will have more decimal places of accuracy. Questions? Okay. Let's have another example. Evaluate integral of e to the minus x squared dx as an infinite series. If this were not given, you will try to evaluate this using the normal way. Unfortunately, you will not be able to do that. Okay? You will not be able to do that. That's why we need this guy here. we need to evaluate this as an infinite series. Solution. So again, we know e to the x, this is sum x to the n over n factorial from 0 to plus infinity for any x here. So this means e to the minus x squared, this is the sum from 0 to plus infinity of negative x squared to the n over n factorial. And this is just the sum, n from 0 to plus infinity, negative 1 to the n, x to the 2n over n factorial. And this is true for any real number. Therefore, we integrate e to the minus x squared dx. This is the integral of the sum, negative 1 to the n, x to the 2n over n factorial, and from 0 to plus infinity dx. This is equal to the sum, negative 1 to the n over n factorial, integral of x raised to power 2n dx, and from 0 to plus infinity. So this is just the sum, negative 1 to the n, x to the 2n plus 1 divided by n factorial times 2n plus 1. N from 0 to plus infinity plus some arbitrary constant c. And this is our antiderivative. Okay? Questions? Okay. Next problem. Find the value of the integral from 0 to 1 of e to the minus x squared dx, correct, within an error of 0.001. Okay? Find the value of the integral from 0 to 1 of e to the minus x squared dx, correct, to within an error of 0.001. Okay? Let's see. If we calculate directly, the definite integral, okay? We calculate directly the definite integral, we have the following. So we have already seen the following from the previous problem. Okay? So from the previous problem, previous example, we have this. There's a plus c, of course. So if we evaluate this, we will have integral from 0 to 1, e to the minus x squared dx. This is just the sum, n equals 0 to plus infinity, negative 1 to the n, x raised to 2n plus 1 divided by n factorial times 2n plus 1. And we evaluate this from 0 to 1. And after the evaluation, take note at x equals 0, this will all disappear. I mean, everything here will disappear. At x equals 0. Okay? At x equals 1, we have just negative 1 to the n over n factorial 2n plus 1 n from 0 to plus infinity. Okay? So, this function here, okay, if we think of this as a function, then we will try to find a way to find the value of this evaluated at something, so that the error will just be so that the approximation will have an error of 0.001. Okay? By the way, there's a question, what about the plus c? It will disappear because we are now doing definite integral here. Okay? Anyway, so let us see. Let us see the actual value of the definite integral is this guy. Okay? Now, here's what we're gonna do. We need the sum, okay? Negative 1 to the n over n factorial 2n plus 1 and from 0 to plus infinity. Okay? This guy here, an alternating series. Correct? So we can use the approximation with the use of alternating series. Okay? So if S sub k, this is just the partial sum n from 0 up to k, negative 1 to the n over n factorial 2n plus 1. Okay? We label R sub k. This is equal to what? The actual sum. Let me write this as your actual sum. So let S be this. So R sub k minus S sub k here. Okay? What else? We write B sub k or B sub n, whatever, B sub k, 1 over k factorial times 2 k plus 1. Okay? Then, the absolute value of R sub k, this will be less than or equal to B sub k plus 1. Okay? Still remember that? So just to recall what I have written here, let's look at this. You have an alternating series, okay? And the sum, okay? It's convergent, alternating series, so it must satisfy these conditions. Then you have your R sub n. It's defined to be S minus S sub n. The absolute value of R sub n will be less than or equal to B sub n plus 1. Okay? So in here, R sub k, it's less than or equal to B sub k plus 1, where our BKs are these guys here. Okay? So if you want to find the exact value of this definite integral here, which is just this guy here, which is this, an alternating series, okay? Find a value of that definite integral, correct to within an error of 0.001. We need to make sure that this B sub k will be less than 0.001. Okay? And we will try to find the value of k satisfying that. So, let us see. We need to find k such that R sub k in absolute values less than or equal to B sub k plus 1. We need to find that k such that this B sub k plus 1 is less than 0.001. So, B sub k plus 1, what is this? This is 1 over k plus 1 factorial times 2 times k plus 1 plus 1. This should be less than 0.001. Okay? Or we get the reciprocals, or we have k plus 1 factorial times, let's multiply 2 times k plus 1. So you will have 2k. And then we have plus 3. This should be greater than 1 over 0.001. But this is what? 1,000. Okay? And then from here, let's just do some trial and error. Okay? Let's start with k equals 1, k equals 2, k equals 3. We will try to choose the value of k, the smallest value of k satisfying this guy here. Okay? So let's see. We have here k plus 1 factorial, 2k plus 3. Okay? And then we have the k here. Maybe let's start with 4. So if we have 4, we'll have 5 factorial times 4 times 2 times 4, that's 8 times 11 here. 5 factorial, that's 120 times 11. Yeah, this one is good. Okay. What is this? We have 1,200 plus 120, 1,320. Okay. This one is greater than 1,000 already. Okay. This one is greater than 1,000. Let's see. Is this the smallest? What about k equals 3? Let's just check. 3 plus 1, that's 4 factorial times 2 times 3, that's 6 plus 3, 9. 4 factorial, that's 24. This is just 216. So what does this mean? K equals 4 will be the smallest value satisfying this. Okay? So we take K equals 4. So what does this mean? With K equals 4, okay, we look at the partial sums here with K equals 4 and then we calculate. Okay? So we have the sum and from 0 up to 4, negative 1 to the n over n factorial 2n plus 1. So what is this? When n equals 0, we'll just have 1 minus. When n equals 1, we have 1 over 3 plus when n equals 2, we have 2 factorial times 5 minus, so n equals 0, n equals 1, n equals 2, n equals 3, we have 1 over 3 factorial times 7 plus 1 over 4 factorial times 9. Okay? So this expression, it's roughly 0.747486772, etc. Okay? This is what I got. Okay? Now, let's try to check the value of this integral from 0 to 1 e to the minus x squared dx. The actual value without doing the um without doing the power series representation. So I'll be using a calculator. So using my calculator, I got 0.746824, etc. Okay? Yep. Look at this. Precise up to 0, 0, 1. I mean 0.001. Okay? We have 7, 4 here. We have 7, 4 here. You have 6 next to 4. In here, next to 4, it's also 7. In fact, after 6, you have 8 in here. In here, you have 4. So even if you round this up to the third decimal place, this will be 747. In here, if you round this up to that decimal place, it's also 747. So roughly speaking, we are within this error if we take k equals 4. Okay? Let's have some more examples. Find the Maclaurin series for cosine x. Find the Maclaurin series for cosine x. Look at this. So solution. We let f of x equals cosine x. Okay? Maclaurin series, it means the center is 0. Correct? So f of x equals cosine x. F of 0, this is just cosine 0, and this is equal to 1. F prime of x, the derivative of cosine, it's negative sign, correct? So negative sine x. F prime of 0, that's negative sine 0, and this is 0. F double prime of x, this becomes negative cosine x. And f double prime of 0, this is negative cosine 0. This is equal to negative 1. F triple prime of x, this is now sine x. So f triple prime of 0, this is sine 0, this is again 0. And look, if we get the fourth derivative of f, we'll go back to cosine. So in here, the fourth derivative at 0, this is 1. And you will continue the pattern. 1, 0, negative 1, 0, 1, 0, negative 1, 0. Correct? Okay? So, how do we see that? F of 4k, so this is f of z, sorry, f, the fourth kth derivative of f, okay, of x, this is always cosine x. If you get 4k plus 1, that's your order of derivative. This will be negative sine x. If you get 4k plus 2, this is negative cosine x. If you get 4k plus 3, you will get sine x. So at 0, at x equals 0, you'll just have here 1, 0, negative 1, 0. So what does this mean? C sub 4k, C sub 4k. This is this guy here, divided by 4k quantity factorial. C sub 4k plus 1. This is just 0. Here, I'll write it as 1 over 4k factorial. C sub 4k plus 2 will get negative 1 over 4k plus 2 factorial.
Sir,
Yes,
where did you get the F4K from?
it's the pattern coming from here. The 0th derivative, the 4th derivative. The next time that this cosine x will appear, it's on the 8th derivative.
Okay.
And the next time will be on the 12th derivative. So the pattern will be 4 times any k. Okay? 4k plus 1. K equals 0, that's first derivative. K equals 1, that's the 5th derivative. It's next here. Then the next one will be the 9th derivative. And so on and so forth. That's the pattern. Okay? And then let us continue with this. 4k plus 3. That's the subscript. So this will be 0 again. Okay? So let us see. We have f of x. Okay? This is at the 0th derivative, we'll just have 1 over the 0 factorial. And then on the first derivative, we have 0. On the second derivative, that's when k equals 0 at this part here. On the second derivative, we have negative 1 there. That's why we have minus 1 over 2 factorial x squared. On the third derivative, that's 0 in here. On the fourth derivative, we have 1 again. So plus 1 over 4 factorial x to the 4. On the fifth derivative, that's when k equals 0 in here. You have 0 here. Sixth derivative, it's from here. So minus 1 over 6 factorial x to the 6. Seventh derivative, it's 0 again. On the eighth derivative, we have plus 1 over 8 factorial x to the 8. And blah, blah. You continue the pattern. That will be the pattern. So if you put this as a series, this will just be the sum. And from 0 to plus infinity of x to the 2n over 2n quantity factorial. Because you only see here even terms. 2 factorial, 4 factorial, this guy here. But look, we are alternating. Positive here, negative here, positive here, negative here. So there must be negative 1 to the n. And I put the exponent n here because you start with n equals 0. At n equals 0, you have positive. At n equals 1, you got negative there. At n equals 2, you got positive there. So let me just rewrite this. This guy here, it's negative 1 to the n x raised to power 2n. And of course, you have that 2n factorial. 2n factorial. So this is your power series representation. And verify that the equality will be true for any x. Check the radius and the interval of convergence of this. Okay? So this is true for all x in the set of real numbers. So again, for this, verify, meaning check or find or determine ROC as well as IOC. So try to remember this. Okay? Try to remember this guy here. Next problem. Find the Maclaurin series for sin x. So what do we have in here? Solution. We know from previous example, we know that cosine x, this is the sum, negative 1 to the n, x raised to 2n over 2n quantity 2n factorial. And from 0 to plus infinity. So what we can do is to get the derivative of cosine x. Correct? Okay. So sine x, this is equal to the negative of the derivative of cosine x. If you get the derivative of cosine x, that's negative sine x. Multiply by negative 1, you will have positive sine x. So this is minus the derivative with respect to x of the power series, negative 1 to the n x raised to 2n over quantity 2n factorial, and from 0 to plus infinity. And if we get the derivative of this, we will have some start with n equals 1 up to plus infinity. And this n equals 1 will be justified. Well, if we look at this guy here, we have the constant part here. So when we get the derivative, that constant will disappear. So you will be starting with the next number. Okay? So in here, we will have negative 1 to the n, derivative of x to the 2n, that's just 2n. X raised to power 2n minus 1 then all over 2n factorial. Okay? Now, recall 2n factorial. This is simply 2n times 2n minus 1 times 2n minus 2, etc. Or simply, this is just 2n times 2n minus 1 factorial. So it means the 2n here that will be on the denominator, it will cancel this guy. So we will have negative sum n from 1 up to plus infinity, negative 1 raised to n, x raised to 2n minus 1, divided by 2n minus 1 factorial. And then we can bring that minus inside here. We can bring it here. We will add a power for n. So this will be the sum, and from 1 up to plus infinity, negative 1 raised to n plus 1, x raised to 2n minus 1 over 2n minus 1 factorial. So in here, we just differentiated. So the interval of convergence will be the same as the interval of convergence of cosine. Okay? So let me put it here again. So again, this part here you need to verify, but it's true for any x. Okay? Let's have another example here. Evaluate integral from 0 to 1 of cosine x squared dx as an infinite series. So again, without this guy here, you won't be able to do this using our standard way, our techniques. So we have to do the infinite series way. So solution. Again, let's just bring this cosine x. This is negative 1 to the n, x to the 2n over 2n factorial, and from 0 to plus infinity. This is for any real number. So cosine x squared, this is the sum from 0 to plus infinity, negative 1 to the n, x squared raised to 2n over 2n factorial. But this is just the sum, and from 0 to plus infinity, negative 1 to the n, x raised to 4n divided by 2n factorial. So this means integral of cosine x squared dx. This is equal to the integral. Sorry, it's evaluated from 0 to 1. So we have 0 to 1 here, 0 to 1 here. We have the sum from 0 plus infinity, negative 1 to the n, x raised to 4n divided by 2n factorial dx. So this is just sum from 0 to plus infinity, negative 1 to the negative 1 raised to n over 2n quantity factorial. Then you integrate from 0 to 1, x raised to 4n dx. So continuing, we will have the sum, and from 0 to plus infinity, negative 1 to the n over quantity 2n factorial times x raised to 4n plus 1 divided by 4n plus 1 evaluated from 0 to 1. So this will just be the sum, negative 1 to the n over quantity 2n factorial times 4n plus 1, and from 0 to plus infinity. Okay? Now, let's have this not so easy exercise. Let f of x be this piecewise function. So e raised to negative 1 over x squared if x is not equal to 0, and then it is equal to 0 if x is equal to 0. Show that f prime of x equals 0. Show that the nth derivative of f evaluated at 0, it's also equal to 0 for all n. So whatever derivative you have, you evaluate it to 0, it's still 0. Show that the Maclaurin series of f is convergent for all real number x. However, the Maclaurin series will only be equal to f when x equals 0. Okay? Let us see. So how do we do this? Let's start f prime at 0. Let's start with that one. So recall the definition of derivative. We'll use that one. We'll use the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0. But in here, since we are evaluating at 0, okay, we'll have f prime of 0. This will be the limit as x approaches 0 of f of x minus f of 0 over x. This is just equal to the limit x approaches 0. Take note that in here we are only approaching 0. So x is not really equal to 0, which means that we are going to use this. So we will have e to the minus 1 over x squared minus f of 0, that's just what? F of 0 is 0 according to this. Okay, according to this. And then divided by x because you have x minus 0. Just to clarify, this denominator here, it's x minus 0. Okay? That's why we'll just have x in here. So what is this? As x approaches 0, 1 over x will go to plus infinity. We have minus in here. So as x approaches 0, e raised to negative 1 over x squared will go to 0. In short, this is just 0 over 0. So maybe we can use L'Hopital's rule. Okay? Maybe we can use that one. So what will happen if we use L'Hopital's rule? We have the limit as x approaches 0. I hope this will work. Otherwise, we'll use uh, the, the reciprocal. But anyway, so as x approaches 0, derivative of e raised to negative 1 over x squared, it's e raised to negative 1 over x squared times derivative of negative 1 over x squared. That will be what? 2 over x cubed. 2 over x cubed. Okay? Now, this is bad because originally we have x in here, but after applying L'Hopital's rule, we have x cubed. It increased. So that's bad for us. So this is what we're going to do. Instead of doing this 0 over 0, we'll get the reciprocals. This guy here, it's still equal to the limit. As x approaches 0 of 1 over x over e raised to 1 over x squared. Sorry, yeah, that's positive in here. And as x approaches 0, both of these will go to, say, 0 from the right, infinity over infinity. 0 from the left, infinity over infinity. Okay? So if we divide that into two parts, let me write it here. So you got 0 from the right or 0 from the left. Okay? What you will get here is infinity over infinity. So you can apply L'Hopital's rule here. If we do that, this is what will happen. So limit as x approaches 0, either from the left or from the right. In the numerator, we will have derivative of 1 over x, that's negative 1 over x squared, divided by, we have e raised to 1 over x squared, derivative of 1 over x squared, that's negative 2 over x cubed. Okay? If we simplify this, we'll just have limit as x approaches 0, either from the left or from the right. If we simplify this, numerator will just become x. Denominator, it's 2 e raised to 1 over x squared. And look at this. This is 0 over infinity. The limit here, it's just 0. And we are done. Okay? So, f prime of 0, this is equal to 0. The second part, we need to get the nth derivative of So we need to get the nth derivative of f evaluated at 0. Okay? That will need a lot of work, to be honest. What you can do, actually, that's the same way that you will do here. It's a valid method. What you can do is to get the derivative of this, okay? And then you get the limit from the left and from the right, okay? So let us try to do that number 2. If x is not equal to 0, then f prime of x, that's just the derivative of e raised to negative 1 over x squared. Okay? So that will be 2e raised to negative 1 over x squared over x cubed. Okay? And then, what do we have? F. So let me put it here to get some space. So, f double prime at 0, this is the limit as x approaches 0 again of f of x minus f prime of 0 over x minus 0. We have shown f prime of 0, it's 0 coming from here. So this guy here, it's just 0. Okay? And then when x not equal to 0, you have this f prime. So let's just write that. So we have the limit as x approaches 0, f prime of x, that's 2a e raised to negative 1 over x over, 1 over x squared over x cubed all over x. Okay? And then similar to what we did earlier, we can rewrite this as we have the limit as x approaches plus infinity, plus 0. I mean, as x approaches 0, again from the left or from the right, you will have here 2 over x to the 4 divided by e raised to 1 over x squared. And this will be, again, infinity over infinity. So we apply L'Hopital's rules. If we apply L'Hopital's rule, you'll just get the limit as x approaches 0. For the numerator, what's the derivative? It's negative 8 over x to the power 5. The denominator, the derivative will be e raised to 1 over x squared times negative 2 over x cubed. And if we simplify this, you will get limit x approaches 0 of 4 over x squared divided by e raised to 1 over x squared. Just simplify it. And again, this will be infinity over infinity. So we apply L'Hopital's rules. We will have the limit as x approaches 0. Derivative will be negative 8 over x to the power 3. On the denominator, we will have e raised to 1 over x squared times negative 2 over x cubed. And look, if we simplify this, this is just the limit as x approaches 0 of 4 over e raised to 1 over x squared. And the limit here, this is again 0. Okay? Questions? So this means that f double prime of 0, this is equal to 0. That's for your second derivative. You can do third derivative, fourth derivative using the same process. Okay? But it will be longer. Much, much longer. So, there could be a simpler way to solve this nth derivative of f. So, just try to find that simpler way if there is any. But in here, what I'm doing is I'm using the definition. So we will skip now all the details for the nth derivative. Okay? So at least this guy we showed. For this, we showed for n equals 2. You can do n equals 3, n equals 4, etc. Or a simpler way, if you have one, you can do that. Let's do this number 3 now. So we are now in number 3. Cn, this will be this guy here. Okay? Cn, it's the nth derivative of f evaluated at 0 over n factorial. This is equal to 0 for all n. Because of 1 and 2. Because of items 1 and 2. Okay? Which means, so the Maclaurin series of f of x is 0. Correct? Correct? This is 0 for all x. If it is just 0, then it is convergent because you have a sum. The sum is just 0. But the Maclaurin series of f, it's constant, but your function f, it is not constant. It's this if if x is not equal to 0. It is 0 when x equals 0. So that's the only time that they are equal. So the Maclaurin series of f only, or Maclaurin series of f equals f of x only at x equals 0.